Welcome back to the Deep Dive. Today, we are diving into a concept that sits right at the intersection of, well, science fiction and some pretty fundamental physics.
Right.
We're asking a question that sounds like it was ripped from a classic thriller. Does the most basic building block of our reality, the electron, have an exact inverse, maybe even a terrifying counterpart?
It absolutely does. And the answer is a definite yes. Based on the material you shared, our mission today is really to get to grips with this particle, the positron.
Okay.
We're going to unpack what it is, figure out why it holds one of the most explosive secrets in the universe, and ultimately why its absence is the reason we exist at all. It's kind of the story of the missing half of the cosmos.
Let's start at the very beginning then. We all know the electron, it's everywhere, it orbits the nucleus, carries that negative charge essential for all chemistry. So what exactly defines the positron, its anti-sibling?
The positron is the electron's partner in crime, or you could say its nemesis. Back in 1928, the physicist Paul Dirac, he basically predicted its existence before anyone had even seen it.
So it was a prediction, not a discovery.
Exactly. He realized the math, the equations for quantum mechanics, they required a particle that was identical to the electron in every way, size, but with the opposite charge, a positive charge.
Wow. So it wasn't found by accident, it was. It was mandated by the math.
That's a great way to put it. It's a perfect twin, just charge reversed.
Yeah.
And that electrical reversal, that one difference, dictates its entire life cycle, which tends to be very, very short.
So we have this positive electron, the positron. If it's a natural part of physics, why don't we see it everywhere? Why aren't there atoms made of anti-electrons orbiting antiprotons?
Because of the single most explosive property in all of physics.
Annihilation.
Annihilation.
Yeah.
If you could build a world of antimatter, the moment a regular matter particle, say, an electron touches an antimatter particle, they undergo what we call the great event.
That sounds intense. What does the great event actually look like on a particle level?
It's the ultimate energy release. I mean, truly. The moment an electron and a positron meet, they don't break apart, they don't combine.
They just stop existing.
They completely cease to exist as particles. They vanish. The matter and antimatter convert their entire mass, totally and instantaneously, into pure energy.
So that's where EMC22 becomes brutally real.
Absolutely. It's the perfect conversion.
Yeah.
When scientists say, this is more awesome than any Marvel movie, they mean the efficiency. There is zero waste, just the total conversion of mass into pure energy, usually gamma rays. Instant light.
Okay, here's where the conversation always takes a turn toward the chilling. We're talking about single particles here, but if you could scale that up,
Right.
if we could hold a tangible amount of antimatter in our hands, what are we talking about in terms of destructive potential?
The energy density is just. It's truly off the charts. It's why science fiction loves it as a super fuel or a weapon. And the sources give us a figure that really puts it in perspective.
It just.
Just 1 single gram of antimatter, if you brought it into contact with 1 gram of regular matter, could unleash enough energy to destroy an entire major city.
1 gram, that's less than a paperclip. Why is that so much more potent than, say, a gram of uranium in a nuclear bomb?
That's the key question. In a traditional nuclear reaction, like fission, you are only converting a tiny, tiny fraction of an atom's mass into energy. A very small percentage.
But not here.
Not here. In an annihilation event, you are converting 100% of the mass involved. It's the efficiency that gives it that terrifying, epic level of power. A few milligrams contain more energy than the largest nuclear weapon ever built.
Okay, so given that extreme implication, the natural question is, if this stuff is so unbelievably dangerous, why aren't we seeing advanced weapons or antimatter-powered spaceships?
Right.
Is it just impossible to make?
That's the friction point, isn't it? Between the theory and the reality. It's why that single gram is still a hypothetical city destroyer. The main problem is cost.
It's too expensive.
And just sheer difficulty. You need enormous amounts of energy to create even 1 particle of antimatter. Way more energy than you get back from annihilating it.
So it's not an efficient power source.
Not at all. And then once you make it, you have to store it. And since it can't touch anything made of matter, you have to suspend it in a perfect vacuum with magnetic fields forever.
So we can only create these tiny, tiny, highly unstable amounts, and it costs a fortune to do so. That makes me feel a bit better about the whole antimatter bomb scenario.
Absolutely. Think about the scale of what we've actually done. Particle accelerators, some of the most complex machines on Earth, have made and trapped antihydrogen.
But how much?
Oh, ridiculously small amounts. We're talking picograms or femtograms. We are nowhere near grams. The most expensive substance on Earth isn't diamonds, it's antimatter.
That really clears up the threat level. But this brings us to the huge paradox we talked about earlier. We actually harness this terrifying, explosive substance, and we use it inside human beings, in hospitals.
We do indeed. And this is the great aha moment for a lot of people. We're talking about positron emission tomography, the PE scan.
The PT scan, I've heard of it, of course.
And that technology is completely reliant on the physics of annihilation.
Okay, so a PET scan. You inject a patient with a radioactive tracer, right? A sugar molecule that emits positrons. But why do that?
Well, that tracer, it seeks out cells in your body that are really active, that use a lot of energy.
So cancer cells, for example.
Exactly. Cancer cells consume a lot of sugar. Once the tracer gets to that target cell, it decays and emits a positron. That positron immediately finds an electron because your body is full of them, and
Annihilation happens right inside the patient's body.
annihilation occurs, yes.
So wait, the medical benefit isn't from the positron itself, it's from the tiny explosion it creates.
That's exactly right. The goal is to create that small, localized explosion. When the electron and positron annihilate, they produce two gamma-ray photons that fly out in perfectly opposite directions.
180 degrees apart.
Exactly. The PET scanner is just a giant ring of detectors, and it's looking for those simultaneous back-to-back bursts of energy.
And by tracing where those two photons came from, doctors can map the exact location of the cancer.
Precisely. It gives you this incredibly detailed functional image that shows you activity, not just structure. It's a beautiful, clever application of some really extreme physics.
But let's go back to the safety question, because I know you're thinking about this. If a gram can level a city, why doesn't even a small amount of antimatter in a PET scan cause, well, damage?
Right, why don't you explode on the table?
Yeah. My body is full of electrons just waiting.
It comes down to two things that make it perfectly safe. First, the quantity is minuscule. I mean, we're talking trace amounts, nanocuries. It's far, far below any dangerous math.
Okay, so the dose is tiny. What's the second thing?
The speed. This is the critical factor.
Uh-huh.
The radioactive isotopes we use are designed to have a very, very short life. The positron itself only exists for a tiny fraction of a second.
How short are we talking?
A microsecond, maybe less. It just doesn't have time to travel far or do anything before it finds an electron, and poof, annihilation. It's all controlled, localized, and happens on a molecular scale.
It's the ultimate example of precision physics, then, taking the universe's most explosive reaction and making it safe enough to, save lives. That is genuinely mind-blowing.
It is. So now let's zoom out. Let's leave the hospital and go to the cosmic mystery, because this is where the positron leads us to the biggest questions in science.
Right. So if the universe is full of matter and the positron is its natural partner, where did all the antimatter go?
This is the central problem. The laws of physics, as we know them, are built on symmetry. Right after the Big Bang, when the universe was incredibly hot and dense, for every particle of matter created, every electron, every quark, an identical antiparticle should have been created with it.
Perfect symmetry, a perfect 50-50 split.
A perfect 50-50 split, yes.
Yeah.
And if you have that perfect mix and everything is churning around in that chaotic early universe, the outcome is, well, it's inevitable.
Total annihilation.
Total annihilation. Everything should have canceled everything else out, leaving behind a universe of just pure radiation. No stars, no galaxies, no us.
And yet, here we are. The observed reality is that the entire universe we can see is built almost exclusively of matter.
The fact that anything survived means that at some point in those first fractions of a second, the symmetry was broken. There must have been a slight imbalance, a crucial one.
How slight?
Scientists have calculated that for every billion pairs of matter and antimatter, there must have been one extra particle of matter left over.
Just 1 in a billion. And that's the residue that built everything we see.
That's it. That tiny asymmetry is the reason for all existence. We are, quite literally, the leftovers of the Great Annihilation. Understanding why matter won is probably the most important unanswered question in cosmology today.
So if that's what happened, what could have caused it? What mechanism allowed matter to just slightly overwhelm its twin?
This is what physicists are chasing. Why did nature have this slight preference for matter? The search is focused on something called CP violation. It's a subtle phenomenon where some particle interactions behave differently if you swap the particle for its antiparticle.
We're talking about physics so fundamental, so subtle, that the tiniest asymmetry in how a particle decays could have set the destiny for the entire universe.
Exactly. And the problem is, our current theories, the standard model of particle physics, it just doesn't account for enough of this asymmetry. The imbalance we see is too big for the physics we currently know.
Which implies there must be something else. New undiscovered laws of physics, or maybe new particles we haven't found yet.
That is the implication. Solving this puzzle of the missing antimatter means finding physics beyond the standard model, something that explains that crucial 1 in a billion preference. If we can nail that down, it opens up entirely new ways of understanding mass, gravity, everything.
So understanding the positron, the anti-electron, it's really the key to understanding the half of the universe that's missing, and why the half that's left is even here.
It is the ultimate search for why we exist. Our entire reality is built on this tiny, fundamental imbalance. The positron isn't some evil twin. It's a constant reminder that physics loves symmetry. But the universe itself is defined by a deep and profoundly important asymmetry.
This has been a powerful deep dive. We started with the theoretical prediction of the charge-reversed positron, then we moved to the terrifying physics of annihilation, where just 1 gram has city-destroying power.
Right.
And then we examined its critical, safe role in medical PT scans, where its incredibly short lifespan is the key to everything.
And we ended on that cosmic scale, recognizing that the overwhelming absence of antimatter in our universe is one of the most profound mysteries there is. We are the result of a subtle asymmetry in the universe's first moments, an asymmetry we still can't fully explain.
So, what does this all mean for you, the listener? If the next great breakthrough in physics is finding the definitive reason for this matter-antimatter imbalance, if scientists discover the force or particle responsible for tipping those cosmic scales, what unintended door might that discovery open for physics, and how drastically could that reshape our entire perspective on the cosmos and maybe our own future?